All right, so the question is regarding using equations with a known Kc value to determine an unknown Kc value. And so the desired equation N2O O2 N2O4.
Did they give us other formation equations?
Yes, they give me 3 others.
Okay.
All right, so we have some equations here that we can choose from. I should bring this up. So what I do in something like this is I want 2 N2Os over here. And so what I'll do is I'll look for an equation that has N2O. And this is number 12. And so in order to get N2O, what I could do is I could reverse the first equation and double it. And so I'm going to reverse equation 1, okay, and double it. So 2 times the reverse of equation 1. And so that's going to give me 2 N2Os here if I reverse this. And an O2 and a 2 N2s. So we'll go to 2 N2 plus an O2. And so if I double it and reverse it, what I have to do is I have to take the inverse of equation 1 and square it. And that would be it. All right, then what I look for is 2 N2O4s, over here. And N2O4 occurs only in one of the equations, yeah. The second one, and I have to double it. I have to reverse and double the second one. And so, yeah, this is 2 times the reverse of equation 2. And so that should give me my 2 N2O4s on the product side. And so I have 4 NO2s, 2 N2O4s. So I reversed equation 2 and then doubled it. Now let's see where we're at here. I have my N2Os and my N2O4s, but I have these NO2s that don't cancel out. Do you see that? And so what I want to do is I want to get rid of these NO2s here, if I can. To get rid of NO2, there are 2 equations I could use. I could use equation 2, which I already used, or equation 3.
3 because you also need oxygen.
Yeah, and so I'm going to use equation 3, and for equation 3, I'm just going to write it as is, but quadruple it. And so this will be 4 times equation 3. And so this will be 4 N2 gas plus 4, actually, O2 plus 4 N2. And so this would be equation 3 to the 4th. All right.
The third equation is 1/2 N2 gas, so now there's only 2 of them if you multiply by 4. The bottom equation next to the line, on the N2 right there, it's actually the original is half N2.
Sorry.
So yeah.
That's correct. Yeah.
Just making sure.
Yeah, that would be right. So assuming that we did everything correctly, the NO2s cancel, the 2 N2s cancel. And then I have 1 O2 over here, and then 4 O2s, so that gives me 3 O2s. So we get our desired equation. And so this one is just going to be K3 to the 4th divided by K1 times K2 squared. You take the square root of that. Take the square root of that. Get K3 squared over K1 times K2. And then just multiply out the numbers. get the correct number of sig figs. Okay, so that's what you do.
So why do you pick the square root of it?
You don't.
But the solutions manual did something different.
What did the solutions manual do?
I cannot remember, but all I just know is it's different.
Actually, there are a number of ways you can solve it, so you don't have to solve it exactly this way. You could use other ways.
Why is K3
Oh, why is K3 in the numerator?
Because we didn't reverse it.
Yeah, we didn't reverse it, and then we just multiply these all together. And so when we multiply, K3 goes out.
Excuse me.
Okay, any other questions? And this, how about other homework questions? Yes.
May I move on to the lab, please?
All right. You have a question about lab?
Yes. Should we use the theoretical yield that we calculated, or should we use the theoretical yield of 9 grams?
No, you should use the theoretical yield that you calculated.
So it's not 9 grams.
Yeah.
Well, why does the book say it's 9 grams?
Did the book say it's 9 grams?
Yeah.
It should be about 9 grams. 11 grams is close enough. Yeah. That's okay. I don't know why they got the yield of that.
I tried it again and again. Actually, it's getting 12 grams.
That's fine. I looked at your calculation, Kelly. It's okay. I'm not sure how they calculated it. They might have calculated it using oxalic acid as a limiting reagent, but it can't be. Otherwise, you'd have dichromate left over. If you have dichromate left over, it's going to cause trouble.
So you just want us to pretty much do the purity test with comparing it to other.
Actually, you know, because of your recrystallization success, I was thinking of making everybody recrystallize it because you got really nice crystals there. And so I think what I'll do, how's that rough draft coming along?
You saw ours.
I saw one, your guys', yeah. You know, don't think of it as too much work because, you know, all you're going to do is just reiterate like what I said about the reactions. That's basically it. Go through the sequence. But I think I might add on an extra step, you know, because recrystallization is a very common technique, but we don't do it here. We don't do it, actually, probably we don't do it in general chem at all. And so I think I'm going to have you guys recrystallize your crystals to see. Just like half of them or, you know, a quarter of them or whatever. Not all of them. We'll talk about that. And so if I'll decide tomorrow, if I do that, then we'll postpone the due date and you can add something about the recrystallization.
Back for number 12 for the last one, when you times it by 4 for equation 3, why isn't N2 4? Because the original equation for N2 was just, the coefficient was 1.
And the original equation for N2 is 1/2 N2 gas plus O2 yields, or back and forth yields NO2 gas. There's a 1/2 in front of it.
So then, okay, never mind.
But the purity, I don't know.
Yeah, we still don't know about the purity. You're right. We don't know. I mean, but the thing is, what do you say about the purity? This is often the case, you know, when you're doing science, right? You always want to get the right answer. You want to just wait, and I'll just wait and get the right answer. But the problem is you don't have access to equipment, or you don't have time, or you don't have money to do this type of stuff, and so you have to cut it. You know, if I had to wait until I got the right answer on everything, I'd still be there, working on my degree. I would never finish. So what you have to do is you take this data, and you might not be the happiest. You know, there are some people who are very lucky, and they get very nice data. very nice data. Everything presents a very clear picture. You know? And so they're out of there. They're out of there quickly. You know, they say if every experiment works, then you're out of there in less than 4 years. You know, the average time's 5, more than 5 years. I think. And so to get a PhD, and so a lot of that time's spent looking at this data that doesn't quite, you know, yeah, it doesn't make you the happiest. So,
Me too. I was
it's
not
ambiguous.
happy with my percent yield.
Well, yeah, percent yield, you can always say, you can try doing a better job at that next time. But there are questions like, you know, if somebody not confronted, but, you know, challenged you and said, you know, you're going to have to offer maybe more substantial proof that, you know, what you think is what you got, right? What you think is what you got, you know, what kind of proof do you have? Well, you know, you look at the reactions. What are all the potential reactions that can occur? So that's why we go through and talk about, you know, the chemistry, what's happening. Otherwise, what else do we have to go on? And then the purity, you know, the purity is just, you're just using the techniques like washing, separation, this kind of stuff, just to ensure the purity. But, you know, there's some stuff that's free that you can do that, you know, I didn't tell you everything because I want to see what you guys can do. And one of the things you guys can do is, and I hinted at this also, right, is use some of the properties of that stuff we tried to synthesize, right? What was it? Yeah, potassium trioxalate of chromate 3. Use some of the properties to verify that it is. So for example, some people got colorless crystals. Is it colorless? You know, it's been synthesized before, it's nothing new. So, all right. What if it were new? How would you determine it? You know, this is something I talked about in Chem 1A in Chapter 2. If it were something new, you didn't know what it was, how would you determine what it is? Kelly, you have a question?
Yeah. What effect would having to add too much ethanol do to the crystals?
Too much ethanol is good. Too much ethanol, you should precipitate out more crystals and improve your yield. And so that's, there's no such thing as too much ethanol. It's just you don't want to start wasting ethanol because ethanol is very expensive stuff. Not really, really expensive, but you just don't want to waste it.
What could lower down my yield?
What could lower down your yield? Lots of things. You know, you just lose some crystals here, lose some crystals there. You have incomplete reaction there, here. And so those types of things lower the yield. In the barium sulfate lab, you wanted a quantitative yield. Quantitative means 100% yield. But in a typical synthesis lab, the yields are much smaller because other things happen and you lose things. And so if you go on to organic chemistry, if you get a 60% yield, that's considered very good. You know? And so the yields it depends on what type of reaction you're doing, what type of chemistry, because some reactions naturally don't go all the way forward. You know, they are, like we're talking here. If you're trying to do a Chem 1B style stoichiometry and get 100% yield, you're going to have difficulty because a lot of them don't. For example, if you mix tin 2 with copper 1, are you going to get 100% yield of copper 2 and tin 4? No, it's impossible. And so those types of things happen. Some reactions aren't 100% forward, so you aren't going to get 100% yield.
But how come people get higher yields than others?
It's just, I wouldn't worry about it. You know, the thing is, it could be a matter of luck, you know, during their crystallization, precipitation step. They just had the right conditions. Maybe you needed to add more ethanol, but you're worried because you're thinking you're adding too much ethanol. In reality, you should have added a much, much more ethanol. A lot of people start to worry when they get, because it says add 10 milliliters of ethanol, so a lot of people want to stop there And each drop above 10 milliliters makes them concerned because they're deviating from the procedure. But, you know, that's not reality. Reality is you add as much. I know people who've added 100 milliliters of ethanol.
Wow.
Yeah, 200 milliliters of ethanol just to maximize their yield. It's no big deal. They could do that. You know, this is the difference between knowing what you're trying to accomplish in a step versus just cookbooking it. The people who cookbook it are just going to add the proper amount, but that's not the proper amount. The proper amount is, yeah, what it takes to maximize precipitation. And so those are all kinds of factors that lead to different yields, but you know, naturally you expect because of you know,
Oh yeah, that happened to us
random error.
yesterday. We're trying to add 4 drops of ammonia, but it didn't precipitate, and it didn't turn basic, so we gotta add way much more than that.
Yes, right. You gotta add way much more. And so every semester I have, well, this is not so bad. Chem 4 is maybe worse, but some people have a hard time adjusting the procedure. Especially, maybe it's okay for the known, but when it comes to the unknown, you have to make some dramatic adjustments to the procedure for the unknown. And some people are so scared they don't want to skip a step in the procedure, and so they go ahead and do it anyway, even though it says, okay, centrifuge the precipitate. So they put it in the centrifuge, there's no precipitate there, and then it says to decant. They try to decant it, and then they come up to me confused saying, I'm trying to decant, but there's no precipitate. I can't separate it. You know, so they're going through, and they want to continue going through all the steps, but there's nothing there. And so you got to tell them, no. I mean, I don't tell them anything because it's the unknown. You know, unknown, you're on your own, so I tell them you're on your own. You got to figure out what to do. You know, but it happens every semester. Somebody comes up to me and asks me, step 1, no precipitate, and they keep adding HCl, adding HCl, adding HCl, right?
And that wastes time.
Yeah, and then it's way too acidic for the next step. Yeah.
But when should you stop adding HCl?
Well, if you get no precipitate, then you should stop immediately.
It'll happen on the first drop.
It should happen on the first drop. What I mean by keep adding HCl is to maximize the precipitation, but if you're getting no precipitation, you might as well just stop. Otherwise, you have to undo whatever you're adding. Which means, so if somebody adds 20 drops of HCl, then in the next step, they're trying to neutralize it with ammonia. It's not going to happen. They got to add something a little stronger than ammonia and a little more concentrated than ammonia to get the pH back up. Yeah. Well, that's the lab. We're going to talk more about the lab tomorrow. So let me finish off. We're talking about that problem we were talking about yesterday. That is with multiple equilibria. The reason we're getting the wrong pH is we aren't considering the other equilibria that are occurring here. And so we have this HCl plus H2O, this hydronium plus chloride. And if we treat this as a Chem 1B style problem, you know, we set up an ice table. We start off with 0.100, well, not 1.0 times 10 to the minus 8 molar HCl. 0 molar, and then let this go. But when we look at the K value is very large. If K is very large, then that tells you that it's pretty much all going. It's 100% reaction. We're just going to assume it's 100% reaction. But is that the only equilibrium or reaction occurring here in water? No. Yeah, even though this is not so significant, it's water colliding with water molecules, which we talked about earlier. You know, at 25 degrees C, do all water molecules have the same kinetic energy? No, there's a small fraction of water molecules energetic enough to create some more hydronium. Did we already set this up? No?
We set the water.
We talked about the pH. The pH of this was 8.0, our original calculation, right? That's impossible, 8.00. It can't be. And so something's wrong. And what's wrong is we're missing what else is happening in here. Did I talk about the molarity of pure water? 55.5 molar.
Where is it concentrated?
55.5 moles per liter of pure water. I talked about that? So this reaction happens to about 4 parts per billion. So if I lose 4 water molecules out of a billion, is that going to change the molarity of water much? No, it's not going to change at all. And so we say the activity is just 1. It's got unit activity. And so, you know, pure liquids and pure solids are the same way. You know, if you have a sugar cube and you eat half of the sugar cube, it's still pure sugar, right? And so the activity, you know, the activity or reactivity depends on the concentration. You know, the more concentrated it is, you know, the more dangerous. And so I have no problem drinking hydrochloric acid. As long as the molarity is like 10 to the minus 8 molar, I'll drink it. No problem. But if it's highly concentrated, then forget it. You know, I'll kill myself drinking it. And so activity is related to the concentration. So here, in pure liquids and pure solids, the concentration doesn't change. Therefore, its activity doesn't change. You know, it's effective concentration. And therefore, we call the activity 1. And in fact, we're going to completely ignore liquids and solids in ice tables. So did we come up with the K expression for this? The K expression is just hydronium concentration times the hydroxide. And so I talked about the K. I think I talked about this. You know, the K for real. This goes for real and ideal. The K, you know, the van der Waals equation works for any gas, whether it's ideal or real, right? The van der Waals equation is going to work. Well, this equation is going to work for any solution or any gas mixture, and that is, you know, the activities of G raised to little g, activity of H raised to little h, etc. The activities of products or the activities of reactants. This works for, you know, if we're close to ideal or if we're far from ideal, it's going to work. And so the activity of solutions is equal or approximately equal to its molar concentration. The activity of gases is equal to its pressure. Activities of liquids are just 1, so this is divided by 1 times 1, or 1 squared. So this is it. And so there are multiple equilibria happening here, and the multiple equilibria are connected. Do you see how they're connected? They're connected by, they produce a common species. There's multiple equilibria, in this case, produce the common species hydronium. And so when we calculated the pH just based on HCl, we were missing some hydronium. Because a pH meter, does a pH meter care where the hydronium comes from? You know, the pH meter says, I'm only going to measure the hydronium content. No, because we know water is pH 7, and all the hydronium comes from water. And so the pH, all the pH cares about is the total hydronium. Did I talk about why our pH was so off? Was our pH so off because we weren't using activities? You know, our pH was 8.00. Was it because we weren't using activities? We should be using activities instead of concentrations, and that's why the pH was so far off? No. In fact, you know, the more dilute the solution is, the more ideal its behavior. And so the reason pH was so far off wasn't because we weren't using activities. You know, if we were to use activity, this should be, the pH is equal to negative log. You know, did I write this equation already? It should be the negative log of the hydronium ion activity. Did I write this one? This equation here would be valid, you know, for the entire range of the pH, you know, from negative to highly positive values. And so if we're at negative 3.6, you know, we'd be using activities, not the, you know, ideal concentrations. Well, that's not the reason. The reason we're so far off is because this is what we call a multiple equilibrium problem. Multiple equilibrium problem, if there's no connection between these, then we're okay. We solve them independently. We would have had the right answer. But in this case, the multiple equilibria problem have something in common. What they have in common is hydronium. And so they have a common product. Well, that shouldn't be a big deal, right? Because what I know is, let's pretend this. This is something we often do. We're going to pretend that the waters haven't collided. And so if the waters haven't collided yet, you know, obviously the waters are going to have collided at 25 degrees C, but we imagine the waters haven't collided. And so we start off at 0 and 0. And then there's going to be a change. We're going to let the waters collide and generate some hydronium and hydroxide. And then we've got to figure out, you know, what the amount of hydronium and hydroxide is. We could figure out what the amount is two ways. One, we could just do it experimentally. We dip in a pH meter. The pH meter measures the hydronium ion concentration at equilibrium, but you know, the pH meter is going to measure the total hydronium, right? And so let's figure out the hydronium from water. The hydronium from water is Kw, we have memorized at 1.0 times 10 to the minus 14. And this is going to equal x squared. And therefore x is equal to 1.0 times 10 to the minus 7.
Excuse me.
Mm-hmm. A question?
No, I just burped.
Oh, okay. So we have this, and then we say it's going to be 1.0 times 10 to the minus 7 molar. And so what I'm going to do is, well, if we need the total hydronium, then that means the pH is equal to the negative log of the hydronium from the HCl plus the hydronium from the water. You see that? The hydronium from the HCl plus the hydronium from the water. And so what we should do is just add up the two hydroniums, right? And so that's what I'm going to do. Let's just combine the two hydroniums like this. So I have this hydronium here. I'm going to combine it with this hydronium here. So plugging it in here, I'm going to have the negative log of the hydronium from the HCl is, I got an idea. Let's write it as 1.0 times 10 to the minus 8 plus the hydronium from the water. The hydronium from the water, I'm going to change the exponent here to 8, minus 8. And so this is going to be 10 plus 10 times 10 to the minus 8. And so this is going to give me negative log of 11 0.0 times 10 to the minus 8. Did we do this yesterday? No.
No.
All right. And so what does that give us for pH? Uh-huh.
Excuse me, how can I get 10 times 10 to the negative 8?
Oh, I just changed this. This is 1.0 times 10 to the minus 7, which is equal to 10 times 10 to the minus 8. So make this one smaller and this one bigger. The coefficient bigger, the exponent small. 6.96. Give me one more digit.
6.958.
959 or 9? Did you round it or I don't want it rounded? Is it 958?
6.9568.
6. Okay. 68.
8. 6.9586.
86.
Yes.
We're allowed, looks like we're allowed 2 sig figs, so I'll just do 6.95 sub 8, giving us 2 sig figs. All right, well, one thing is good. The one thing that's good is now this is no longer basic. This is acidic, and it's just slightly acidic. This is why I would drink this water, but there's an error in my calculation.
Why is it sub 8?
It's just the next figure.
Yeah.
The rounding factor.
So then I'd round it.
6.696.
696. I round it to. I'm just showing the. I'm carrying extra digits. Hmm? Well, there's an error in my setup. Can you find the error that I made? Times 10 minus 7. Favor is going to the left on the top.
The HCl, you just assume the reaction line.
Oh, 100% to the right. Yeah. We do that. We make that assumption the reaction goes 100% to the right and then fix it later. This is just standard procedure. When the K, this is why there are numbers for these K values. Over here. There are numbers for these K values, but we ignore the numbers and just assume it has 100% forward reaction. And then as you'll see later, we fix it by letting the fluid react to that. And so it's just the way that traditionally it's been solved, you know, and so we'll just follow that method. And so the problem isn't because of this, actually, this step here. You know, what do we do? How do we usually check our answer? How do we check our answer? Yeah, we just make sure that, you know, the equilibrium concentrations, you know, multiply out to Kc or whatever. Or if we have equilibrium pressures, we just make sure they multiply out to Kp. Right? And so when I look at this, I would double check these concentrations. The way I double check it is, just multiply these two, and it should equal Kw. Does it? It does, right? It's 1.0 times 10 minus 7 times 1.0 times 10 minus 7 is going to give me 1.0 times 10 minus 14. But there's a problem. The problem is does this equilibrium care where the hydronium comes from? No. In this equilibrium, we're looking at the total hydronium here. And now the total hydronium has changed, because the total hydronium is no longer this. See? And so the problem is this. If I have a system at equilibrium, this is a system at equilibrium, right? And I add more hydronium to that, then this is what we call Le Chatelier's principle. Le Chatelier's principle says it's no longer going to be at equilibrium. In fact, you know what the total hydronium is now? The total hydronium is now 11 times 10 to the minus 8. It used to be 10 times 10 to the minus 8, but now it's 11 times 10 to the minus 8. If this is 11 times 10 to the minus 8, then 11 times 10 to the minus 8 times 1 times 10 to the minus 7 is not going to equal 1.0 times 10 to the minus 14. In other words, what we have is a situation where we have Q is greater than K. If Q is greater than K, which direction does it? It's going to shift backwards, right? And so if we add more product here and increase the concentration, then it's no longer going to be at equilibrium. And Le Chatelier's principle says it's going to shift back to the left. When it shifts back to the left, it's going to change this concentration. In fact, it's going to lower this concentration, right? And so we haven't really calculated. We didn't factor in Le Chatelier's principle here. We just added up the hydroniums, assuming that they were independent of one another, but they aren't, because it's all in the same beaker. And so this is not going to work, unfortunately. We can't just add these two here. And so what we have to do is we have to solve these two equilibria simultaneously. That just means at the same time for a common hydronium. That is, we have to put both of these together so that the hydronium I get at the end here is the same as the hydronium I get at the end here, and it's all in equilibrium. It's got to be a mutual equilibrium. And so the hydronium I get here has to satisfy the equilibrium here, and the hydronium I get here has to be exactly the same and satisfy a totally different equilibrium here. Does that make sense? And so what we do is we solve a system of two equations for the common hydronium. Now, what do you think of that, solving a system of equations? This is more work, and so we try to find tricks to avoid doing math, basically. And so the trick that we're going to do is we're going to try to solve this stepwise instead of simultaneous. Okay, so we must solve these equilibria simultaneously for a common hydronium concentration. Unfortunately, solving equilibria simultaneously is a lot of work. And so in this chapter, we're going to work on trying to solve them in a stepwise fashion. In a stepwise fashion, it is a heck of a lot easier. And so a lot of work. And so this is a trick that it doesn't always work. But if it works, it's going to make the calculation much easier. And so try to solve in a stepwise fashion. Stepwise fashion works under these conditions. If step 1 has a much bigger k value than step 2. And so if step 1 has a k value that's, let's say, 3 orders of magnitude bigger than step 2, then it works pretty well. If step 1 and step 2 have k values that are comparable, then it fails. And so we need this. We need this. Each subsequent step is much smaller in magnitude than the previous, etc. There could be many steps to this. All right, so if we have this scenario, then what happens is this. The subsequent steps do not upset the equilibrium of the previous step. If they do, that is, if the subsequent steps do upset the equilibrium of the previous steps, then you must solve simultaneous. And so this is our test usually. We just look and see, did step 2 screw up step 1's equilibrium? If not, then we can kind of do it differently. This fashion. All right, so let's try to solve this stepwise and see what happens here. Step 1's pretty easy because, k is large. K is large, we just go 100% forward. Now, how do I handle step 2? For step 2, there are 2 ways that we can do a Le Chatelier's type calculation, because that's what's going to happen. Step 2, option 1, would be a Le Chatelier's perturbation. And so what we do is we do this, H2O liquid plus H2O liquid. This forms hydronium and hydroxide. And so what Le Chatelier's principle says is that a system at equilibrium. So we're going to make this at equilibrium, 1.0 times 10 to the minus 7 molar, 1.0 times 10 to the minus 7 molar. And so we have a system at equilibrium is perturbed. And so what we're doing is we're adding additional HCl. And so how much HCl are we adding? We're adding 1.0 times 10 to the minus 8 molar, which would be 0.1 times 10 to the minus 7. Yeah, 0 times 10 to the minus 7 molar. And we're not adding any hydroxide, so we're adding some more hydronium. This is from HCl, from step 1. And so what we have is it's no longer going to be at equilibrium, so I'm just going to call it my new initial condition. This is going to be 1.10 times 10 to the minus 7 molar, 1.0 times 10 to the minus 7 molar. We already know which way this is going to shift. Le Chatelier's principle says it's going to shift to the left, right? We increase the concentration of the product. So this is going to be minus X molar, minus X molar. And so at equilibrium, we're going to get 1.1 sub 0 times 10 to the minus 7 minus X molar, and 1.0 times 10 to the minus 7 minus X molar. All right, so we solve for x. So we know that kW is equal to 1.0 times 10 to the minus 14. And this is going to equal 1.1 times 10 to the negative 7 minus x times 1.0 times 10 to the minus 7 minus x. Do you have a calculator that solves the quadratic equation?
Yeah.
Yeah? Okay, then what you can do is you get it in quadratic form. Or I guess you could use successive approximations. I'm not sure which one's going to be quicker. Probably getting in quadratic form. And then once you're in quadratic form, you can either hand punch it or you can just use your calculator. Hopefully you have the quadratic solver. If you have the quadratic solver, then it's easy. And so this is a Le Chatelier's style. And these start to appear in chapter 15. So I skipped it, jump ahead. We have a system at equilibrium, we perturb it, we have new initial conditions, and it's going to re-establish an equilibrium. The new equilibrium that it establishes is kind of interesting because, you know, compared to the original equilibrium, the hydronium is going to go up, right? And so in the new equilibrium, the hydronium increased, the hydroxide decreased from the original. But from the perturbed, the hydronium decreased and the hydroxide decreased. And so the change depends on what initial position you're looking at. And so this is always a trick question on multiple choice. You know, did the hydronium increase or did the hydronium decrease? You can't answer that because you would have to know, well, what are you talking about? Are you talking about did the hydronium increase or decrease from the perturbed concentration or from the original concentration? That has to be clarified first. Does that make sense or not? So this is some math, but at least you have the quadratic formula. But this is too much math. I never solve problems using Le Chatelier style perturbation like this. Never. Because there's a much easier, much quicker way to do this type of problem. The much easier, much quicker way to do this problem is option 2. Option 2 is to reset. This is called a common ion type problem. And essentially all we're doing is just resetting. And the way we do this is like this. Rather than starting here at equilibrium, I'm going to just reset these to 0. In other words, I'm going to just say nothing's collided yet. And so I'll just push all these ions back to water. And so when I do it via reset, I'm looking at step 2 again here. And so I have H2O liquid plus H2O liquid. This is going to give me hydronium and hydroxide. And so I'm going to reset. I'm going to imagine that no water has reacted yet. And so the initial from water is 0 molar and 0 molar. You know, it was at equilibrium, but just reset it. Because it doesn't matter because it's going to equilibrate anyway, right? As long as I don't lose atoms. I'm not losing atoms. I'm just pushing them all to liquid water. Liquid water is pure, so just got to make sure. And so that's the initial. And then I'm going to add the HCl, you know, add the hydronium from HCl. And so this is the initial from the HCl. The initial from the HCl, you know, I'll just take this here and then drop it in here. And this is going to be 1.0 times 10 to the minus 8 molar. And 0 molar for hydroxide. There's no hydroxide being produced. And so my new initial conditions are going to be 1.0 times 10 to the minus 8 molar hydronium and 0 molar hydroxide. Now, this is what we call a common ion. A common ion. What a common ion does is it inhibits the formation of hydroxide, essentially. By doing this. There's one way to imagine the effect of a common ion. The common ion is like hydronium. Hydronium loves hydroxide, right? So you can think of this as like a predator here. If you have a high initial concentration of, let's say, lions, you know, and the hydroxide's the deer or whatever they eat. You know, that hydroxide concentration can't get as high as it originally could. And so, in other words, we are not going to have as much water. You know, in pure water, it's 4 parts per billion, but we're going to have less because we can't build up a high concentration of hydroxide. This hydroxide concentration cannot grow to 1.0 times 10 to the minus 7 molar. There's just too much hydronium around, and it's going to eat it up. Does that make sense?
Yeah.
And so here, the change is going to be plus X molar. Plus X molar. I know what X is normally. X is 1.0 times 10 to the minus 7, but it's going to be less than 1.0 times 10 to the minus 7 molar because of what we call the common ion effect. The common ion effect is going to inhibit the forward reaction. And so at equilibrium, we're going to have 1.0 times 10 to the minus 8 plus X times X molar. Now compare the math. We're going to compare the math here. Actually, I erased it, but I think you have it written down. 1.0 times 10 to the minus 8 plus x times x. Which one's easier to solve? Yeah, this one. This one's so much easier to solve. That's why I never, resetting gets rid of some binomials. If you got two binomials, you got to multiply out. That's a pain in the butt, right? And so if we can get rid of just one binomial, you've saved yourself a lot of time. So that's one of the reasons we reset. The other reason is, well, actually, that's a big reason here. It just makes the math a lot easier. Rather than doing Le Chatelier's perturbation, we just reset it and just do the common ion, quote unquote. All right, now when we solve this, actually, we can do one more thing to this. We might just try the simplifying assumption. Right? Let's just go ahead and try the SA. I'm going to try it. I'm going to say that x is much smaller than 1.0 times 10 to the minus 8. If that's the case, then this is going to be even simpler. It's just going to be 1.0 times 10 to the minus 8 x is equal to 1.0 times 10 to the minus 8. Oh, not 10 to the minus 8, 10 to the minus 14. And therefore, x is equal to, don't even need a calculator for this, x is going to equal 1.0 times 10 to the minus 6. Okay, let's measure or calculate the percent change. The percent change is equal to the change, which is going to be x, 1.0 times 10 to the minus 6, over the initial. The initial is 1.0 times 10 to the minus 8 times 100, which is just 10 squared. So this is going to be 10 to the minus 6, 10 to the minus 8 would be 10 to the positive 2. It would be 10 to the 4th percent, which is huge. It's way greater than 5%. So unfortunately, the SA failed. SA failed. I still have to do a quadratic. So let's get this into quadratic form. This is going to be x squared plus 1.0 times 10 to the minus 8x minus 1.0 times 10 to the minus 14 is equal to 0. Kelly left. Who else has the calculator with the quadratic solver? I don't want to do the quadratic. Who has the calculator? All right. Who's good at solving the quadratic equation? Nobody bought the calculator that solves the quadratic formula? Oh, Jasmine, you have it, right? Okay. So plug in this for A. A is going to equal 1. B equals 1 times 10 to the minus 8. And C is negative 1 times 10 to the minus 14. Might as well get practice using it, because you have to solve a lot of quadratics in this chapter.
9.51.
Okay, 9.51
10 to the negative 8.
times 10 to the negative 8. Okay, that's right. All right, so what we're going to get here is this. The hydronium ion concentration at equilibrium is going to be it's going to be 1.0 times 10 to the minus 8 plus x. X is 9.51 times 10 to the minus 8. So take a look at this. This is going to give us 10.51 times 10 to the minus 8 molar. So take a look at this. About roughly 95% of the hydronium came from water. And only about 10% of the hydronium comes from the HCl in this solution. How do we double check this answer? Well, the way we're going to double check it is just to make sure that these concentrations here multiply out to 1.0 times 10 to the minus 14. And so take 10.51 times 10 to the minus 8 times 9.51 times 10 to the minus 8, and hopefully that comes out to 1.0 times 10 to the minus 14. Does it? Let me double check this. What did you get?
You get 9.98 times 10 to the negative.
Okay, 9.98 times 10 to the negative 15, which will just move the decimal. This is going to be 0.998 times 10 to the negative 15, which is
Oh, yeah, you got your decimal. There you go.
which is 1.0 when we drop that 8 times 10 to the negative 14. It works. So this is good because this total hydronium satisfies this equilibrium. But you know, in step 1 we have an equilibrium as well. And I just increased the amount of hydronium. So if I increase the amount of hydronium in step 1, then we should have a Le Chatelier shift back here, right? And so if we have a Le Chatelier shift back here, then we should factor that in. But one thing about this, K is very large, you know, so if we're to calculate Q, with the increased hydronium ion concentration, Q is still going to be less than K, and so we're still going to be all right. In other words, this is a one-way reaction. In a one-way reaction, Le Chatelier's has no impact. And so, how should I phrase that? Did I say ignore Le Chatelier's? I don't really ignore it. It just, Le Chatelier's has no impact on this. It doesn't apply, yeah. One-way reaction. Le Chatelier's does not apply. Okay. All right, actually we don't have much. I guess we have some fun. So what we can say here is this. Let's summarize. How much hydronium is going to be in this beaker? If I have a beaker that's labeled 1.0 times 10 to the minus 8 molar HCl, let's figure out what's inside this solution. So this is called 1.0 times 10 to the minus 8 molar HCl. All right, the first thing I look for is, do I have any HCl molecules? You know, just molecules of HCl. The total concentration is this, that's correct. But the concentration of molecules, I look here. The concentration of molecules ends here, and it's going to be 0 molar. And then I go on to the hydronium ion concentration. What is the hydronium ion concentration in my HCl? Is it 1.0 times 10 to the minus 8? No. Is it 9.51 times 10 to the minus 8? No, it's 10.51 times 10 to the minus 8. And so the hydronium ion concentration, 10.51 times 10 to the minus 8 molar, comes at the end of step 2. And so what happens is, from step 1, we carry this concentration all the way into step 2 here. And so that's where this hydronium ends up. The chloride stops here. We don't carry the chloride into step 2. And so the chloride concentration is going to be 1.0 times 10 to the minus 8 molar. And what am I missing? The hydroxide concentration. The hydroxide ion concentration comes entirely from water, and it's right here, 9.51 times 10 to the minus 8. All right, and then we're done. So I talked about two ways, the two additional techniques that we use to solve a Le Chatelier style perturbation on the ice versus a reset / common ion style method to solve this. All right, you're going to have to solve Le Chatelier style perturbations quantitatively and qualitatively. And so let's take a look at some qualitative Le Chatelier style problems first.
So, a question. When we added the hydronium from the HCl and the H2O by itself without using the Chatelier or whatever, we got 6.958
Yes.
as a pH.
Yes.
And now you get 6.98. Is that a big difference?
Yes.
Yeah.
Yeah. What is the new pH? What is actually? That's what right over here. The pH. What did you calculate, David? 6.978.
978.
And our previous pH was 6.958.
958.
And so this is going to yield a pH of 6.98 versus the previous pH was 6.96. Is it a big difference? No, barely any difference, but at least we're solving it correctly. It could be a much more significant difference in certain problems. Let's see. But it's much better than a pH of 8. A pH of 8 is very,
Very
Could we use that approximation for when K is very large? Just use the addition,
when K is very large, use the addition.
or is there a circumstance where we can use that approximation adding?
No,
No,
we're never going to add.
we're not just gonna add it.
We're never just going to add them. We don't, what I did, the first way I solved it is I solved the two independently of one another and then added them together. You can never do that. We can add them in this way. This is adding them. You know, this is from the HCl, this X is from water, and then we can add them together. But we can't solve them independently. Unlike stoichiometry, if somebody asks you what the total sodium ion content is from sodium chloride and they had some other sodium salt, like sodium phosphate, then you can add them together. No big deal. That's in stoichiometry in chapter 3 and chapter 4 of the book. Let's skip Le Chateliers. Let's look at some examples of Le Chateliers. Let's go. That's right. I gave you one homework assignment. This is Le Chatelier's calculation, chapter 15. And the easiest thing to do for this is to reset it. This is it. Number 40 is a system at equilibrium, and then you perturb it by changing the volume, which changes all the concentrations. So the easiest is to reset it. Let's take a look at some qualitative Le Chatelier's style predictions. Continuous removal of one of the products of a chemical reaction has the effect of causing the reaction to go to completion, 100%. Explain this fact in terms of Le Chatelier's principle. So, in terms of Le Chatelier's, if we continually remove, like the water, it's going to continue to flow by drying. Although that one would be hard to get a completion. We can represent the freezing of H2O liquid at 0 degrees C as H2O liquid, density 1.00 grams per cubic centimeter, to H2O solid, density 0.92. Explain why increasing the pressure on ice causes it to melt. Okay, so what Le Chatelier's is not just concentration, but its volume will have an impact and pressure. And so basically, if we look at this, higher pressures will favor the more dense phase or the less dense phase. Higher pressures. Higher pressures favor the more dense phase. Should. And so why increasing pressure on ice causes it to melt? Yeah, because water is higher density than ice. So this isn't gonna phase it. So it just pushes it to the left. Explain how each of the following affects the amount of hydrogen present in the equilibrium. So we're looking at the amount of hydrogen. If we raise the temperature of the mixture, well, this is exothermic. And so raising temperature would be, would it favor exothermic processes or would it favor endothermic processes?
Excellent.
It favors endo. The way I always remember this is ice. Yeah, if you raise the temperature, does that favor melting or does that favor freezing? It favors melting. Is melting endothermic or exothermic? Endothermic. And so this is the way I always remember. So increasing temperature always favors the endo. Well, this is exo, therefore it's going to favor the reverse reaction. The reverse reaction is endothermic. Introducing more H2O gas. If we introduce more H2O gas, then that's going to increase the reactants, which is going to force it to the product. Now, if this were H2O liquid, it wouldn't affect it because, you know, it doesn't change its concentration. It's still 55.5 molar, roughly thereabouts. So no impact. And it's the concentration that has an impact. And so, because it's a gas, it has an impact. Doubling the volume. Okay, if we double the volume, then that favors the side with more moles of gas. And so if we look at this, this has 4 moles of gas, that has 4 moles of gas. So if we double the volume, then there's no impact on this equilibrium because, yeah, it won't change. Adding an appropriate catalyst. A catalyst speeds up both the forward and the reverse reaction, so that has no change on it as well. All right, let's take a look at this reaction here. This is different. This is a free radical. You know what free radicals are? They just have a lone electron. We call them dangling bonds. Dangling bonds, they want to bond to something. And so you don't see it here. C5H8 is a free radical. There's a dangling bond, a lone electron in this. Raising the temperature of the mixture. Raising the temperature of the mixture will shift it to the right. It's endothermic forward direction. Introducing more C5H6. More C5H6 will push it back. Doubling the volume. Doubling the volume will favor the side with more moles of gas. So this has 2 moles of gas total. This has 3 moles of gas. So doubling the volume will shift it to the right.
Right.
You could also do that using a Q calculation because if you double the volume, then you change all the molarities. When you change all the molarities, then you have to recalculate Q to see if it's still at equilibrium. What you're going to see is that it's either going to be too small or too big, and it's going to favor the side with more moles of gas. Adding an inert gas such as helium. If we add helium to this, does helium participate in this? No.
No, it's a spectator.
It's a spectator, so it has no impact. And so those are the types of things we do qualitatively, but quantitatively, it's like this. We increase the hydronium, now we've got to recalculate the new equilibrium, right? We increase the hydronium, well, it was at equilibrium, now it's no longer at equilibrium. We have 2 choices. We do Le Chatelier's perturbation style, ice, or we do a reset. Reset's way easier. And we're always going to do a reset. All right, so let's try another problem here and see. We're going to try a problem from your homework. And we're going to do the problem from your homework, but I want you to compare it to the book's answer and see what the book did wrong.
Uh-oh, so you can't use the solutions manual in this.
Do not use the solutions manual for this. And you should be able to figure out what the book did wrong. It should be readily apparent what they did wrong.
Well,
Oh, no wonder. I'm in the wrong chapter. Sorry. You'd be in chapter 16. it's gonna be number 89. So we have a choice. We could either do HCN or aniline. Aniline, do you recognize that? That is a amine. Amines are, they're like ammonia-like. Which one do you want to do? Do you want to do A, hydrocyanic acid, or B, aniline?
A.
A, hydrocyanic acid? Okay, let's do that.
Easier. Formula.
We'll do bases in a minute. But we're going to do A. Determine the pH of 1.0 times 10 to the minus 5 molar HCN. So this is number 89A. 1.0 times 10 to the minus 5 molar HCN. Sometimes it happens, you know, there are a lot of errors in the solutions manual. There's like 4 or 5 different people working on it.
Oh.
It doesn't get checked so thoroughly, but all books have this kind of stuff happen. So the first thing we need is the K value for HCN. And the K values, there's a pretty comprehensive list of K values in Appendix D. And also there's a bunch of K values in the chapter 16 and chapter 17. And so we're just going to go to Appendix D. Look at the K values, you know, there's different names, you know, ionization constants, or acid dissociation constants, acid hydrolysis constants. But we're looking for hydrocyanic acid. So we see acetic, these are just alphabetical, so we'll just go to H. Hydrocyanic acid. Here's hydrocyanic acid HCN, 6.2 times 10 to the minus 10. So, 6.2 times 10 to the minus 10. And then, what's the other equilibrium happening here? Water. And so we got H2O. That's KW is 1.0 times 10 to the minus 14. And so we have 2 equilibria. Which one should we do first? This step 1. We want to do this stepwise because, as I said, stepwise is easier than simultaneous. Yeah, we'll start off with HCN. It has a bigger K, right? Stepwise looks like it'll work, doesn't it?
Yeah.
Yeah. And so, yeah, look at the difference in Ks. This one's 4 orders of magnitude bigger or something like that. And so this is HCN plus H2O liquid. I call this the acid hydrolysis constant because, you know, it's acid plus water. I don't call it the acid ionization because acid ionization, you would ionize it into H plus and CN minus, like up there, you know. But I do it like this. This is going to form hydronium and cyanide. One of the K values up there. And so we started off assuming nothing's happened. You know, 1.0 times 10 to the minus 5 molar HCN, 0 molar hydronium, and 0 molar cyanide. So essentially nothing's happened. And now I let it collide with water. When I let it collide with water, then I'm going to lose some HCN. Not all of it, because K is not large. If K were large, I'd lose all of it, right? But K is kind of small, so I'm just going to lose a fraction of it. So this is going to be plus X molar, plus X molar. I don't know what X is yet. And so at equilibrium, it's going to be 1.0 times 10 minus 5 minus X molar, X molar, and X molar. All right, let's solve for X here. We solve for X, so I get Ka equal to hydronium ion concentration times the cyanide concentration divided by the HCN concentration. When I did my ice table, water, I automatically ignored water, right? We ignore water for liquids and for solids. And so this is going to come out to X squared divided by 1.0 times 10 to the minus 5. And this has got to equal 6.2 times 10 to the minus 10. I have a good feeling that the simplifying assumption might work. The reason I have a good feeling it might work is because of the small k value. The small k value should mean that the change is small. But then I have a bad feeling it might not work. Why would I have a bad feeling it might not work? The bad feeling is, am I dealing with a large swimming pool of initial? No, I have a very small. So even if I lose a little bit, it's a little bit of a little bit, which is significant. But anyway, I am still going to try it. I tried it too early here. I'm going to try the SA by assuming that x is much smaller than 1.0 times 10 to the minus 5. And so this is going to simplify into x squared over 1.0 times 10 to the minus 5, which means that x is equal to, you know, it doesn't take that much time to try the simplifying assumption. If it fails, it's all right. So what does x come out to? 7.87
Times 10 to the negative 8.
times 10 to the negative 8. Okay, so that means the percent change is the change x over the initial. So it's going to be 7.87 times 10 to the minus 8 divided by 1.0 times 10 to the minus 5 times 100. So what does that give us? Here. 87. 10 minus 3, 10 minus 1. 0.787%. That's okay. Right. It would be better if we use the quadratic, but this is close enough, I think. So let's go ahead and use it. And so my HCN concentration is going to be 1.0. Actually, you know what? I'm going to write this in decimal form. My HCN concentration is going to be 4 zeros, 1, 2, 3, 4, and then 1 0. And then I'm going to lose, all right, this is 787, so I need 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros, and a 787. So I'm going to carry some extra zeros here. Then do the subtraction. So this is 10, this is going to be 3, 9, this is going to be 1. Oh, this is not significant. 9, this is going to be 2, 9, 9, 0, 0, 0, 0. 2, 3, 4, 5, 5 zeros, 9. Does that look right? Okay, did I lose that much? No, I didn't lose that much here. And then the hydronium ion concentration is just going to be 7.87 times 10 to the minus 8 molar. And the cyanide concentration is going to be 7.87 times 10 to the minus 8 molar. Okay. But actually, this is not the end for the hydronium concentration, right? This hydronium concentration is not my total hydronium, because I get hydronium from water also. And so I need to factor in the hydronium from water. So that's going to be my step 2. Right. In step 2, I have 2 choices. I could do it a Le Chatelier style, or I could just reset the water to 0 and then add the hydronium. I'm going to reset. You know, this is a common ion style problem. And so it's going to be H2O liquid plus H2O liquid. This is going to give me hydronium plus hydroxide. Okay, so what I'm going to do is I'm going to take this from step 1 and move it into step 2 here. So that's my 7.87 times 10 to the minus 8 molar, and then I'm going to have 0 molar here. So this is from, I'll just write it out, from step 1. Okay. And then from water, we assume nothing's happened yet, and so it's going to be 0 and 0 from water. Usually I write water first, but in this case. And so initially I'm going to start off with 787 times 10 to the minus 8 molar plus 0 molar hydroxide. So this is my initial. The change is all going to come from water. Now pure water doesn't show up in the ice. And so now I'm going to let the waters collide. They're going to make some hydronium and some hydroxide. They aren't going to make as much as they normally would, you know, because of the predator is here. The predator is going to eat the hydroxide, basically, right, and keep the population down. And so it's not going to make as much. The change is not going to be so big. 787 times 10 to the minus 8 plus x molar, and then x molar here. Okay, and then I go over to kW here, and then just plug it in. 787 times 10 to the minus 8 plus x times x. And then I'm going to use the SA. If I use the SA, then this is going to be approximately equal to 787 times 10 to the minus 8 times x, which is equal to kW, 1.0 times 10 to the minus 14. And therefore, x is about equal to what? One point three.
Yeah, I have 1.27 if you want to.
No, I want it like that. 1.27 times 10 to the negative 7. Okay, assuming the calculation is correct, then we can calculate the whole hydronium. The hydronium from step 1 is here. The hydronium from step 2 is plus x. And so this is going to equal the hydronium from step 1, 787 times 10 to the minus 8, plus the hydronium from step 2. Hydronium from step 2, we're going to make it 10 to the 8, so it's going to be 12.7 times 10 to the minus 8. And so this is going to give us 20.57 times 10 to the minus 8.
Excuse me, why is selenic acid a strong acid?
We'll talk about why some things are strong acid and some things are weak acid later. We haven't gotten there. We're just going to use the numbers right now. Later on.
For the first step, for how you got the hydronium atom concentration,
Yeah.
why didn't you just straight cross multiply it out? Could you, or did
What do you mean by cross multiply?
you did the whole, you did the same thing, if you do that, you do the
Oh, why didn't I use a quadratic?
yeah, just like multiply out the quadratic and solve for x.
If it gives you the same answer, then
It's fine.
it's quicker.
Right.
Yeah. If that percent starts to grow bigger and bigger, then you're better off doing the quadratic. Yeah. You know, getting to 0.8, 0.7% is kind of big. We're introducing error, but it's okay according to our criteria. And so how do we double check these? We got to make sure the equilibrium, that this hydronium, this is the total hydronium that has to satisfy both equilibria. And so over here, this is not our hydronium anymore. Our hydronium is 20.57 times 10 to the minus 8 molar. And so because both of these equilibria are in the same beaker, and the total hydronium is just the total hydronium, it doesn't matter where it came from, that both these equilibria have to be satisfied by 20.57 times 10 to the minus 8 molar. How can we double check this? We double check by calculating K. So for example, here, we make sure that these concentrations multiply out to give us a K of 6.2 times 10 to the minus 10. And so we calculate the K. This is called our double check. We double check K. And over here, we're going to double check K as well. These two have to multiply out to 1.0 times 10 to the minus 14. Well, these two will multiply out to 1.0 times 10 to the minus 14, but these three will not. These three are going to deviate significantly from 6.2 times 10 to the minus 10. And so what that means is that step 2 perturbed or upset step 1. In other words, if step 2 changes step 1's equilibrium, then we can't solve it stepwise. We cannot solve this stepwise. You could do the calculation on the you'll see. We have to solve this simultaneously, unfortunately. And so how do we solve? Oh, in reality, we're supposed to solve every single problem simultaneously, but it's too much work.